to also have you guys make sure that you're able to follow me on that platform. If you all need any help, further help, I'm on TikTok and I'm on YouTube. Okay, so this is the channel here. I'm going to go ahead and screen share so you guys can see my screen and see what I'm going through today with my notes. Okay, so let me go ahead and screen share. Okay, there we are. Here we are. And let me make sure everything is straight. Let's see. Okay, I think it is. Okay, hold on, y'all. Okay, let me pause y'all for a second. Okay, let me pause y'all for a second. Okay, there we go. It's up, but I need to make sure it's up that where everybody can see it. So hold on. The screen is black for a reason, so don't hesitate. Don't hesitate. The screen is black for a reason. I'm trying to make sure that all the settings are correct and good to go. Yep. Okay, there we go. Okay. And we're also giving everybody the opportunity to get on in the building as we go through our lesson for today. Okay, so I hope you guys are ready to learn because I'm ready to teach. Let's go ahead and get started right now. So those of you guys that are in chemistry, what are you all working on right now in chemistry? If you are taking chemistry, tell me in the comments below what you guys are working on right now for today. Okay, so I hope. Okay. Yeah, we're good to go. All right. Okay. All right, there we go, guys. We're good to go now. All right, now, so in chemistry this semester, a lot of you guys have been hitting me up trying to get extra help on things that you all don't quite understand. So although we're coming to like the last, for most students that are taking chemistry, if you took chemistry, if you've been in chemistry since January, then I can tell you most of you guys right now have about a month to go. Okay, so in about 4 to 6 weeks, you should be ending chemistry, depending on where you're left at with your chemistry class. So what I've got right here, of course, are things that you may not know. Okay, Robbie says specific heat capacity. Okay, okay. Specific heat capacity is what you guys are learning. Well, I know several of you guys have hit me up and wanted me to do a video on the gas laws. So that's what I'm doing today. So we're going to actually get into the gas laws, and we're going to also use gas law stoichiometry as well. So what you guys may not see on here today, I'm going to be doing over the course of this week. So anytime I start a lesson off in the very beginning of the week, I always go through that entire lesson or that unit throughout the whole week so that students who may be picking up this information halfway through, they're able to get that along the way. Okay. So what I've got for you guys deals with the gas laws. And if you have questions, of course, let me know. If you have questions outside of this information, guess what I want you to do? I want you to wait until the very end, like the last 15 minutes or so, to ask questions. And if it takes me longer than 3 minutes to answer your question, we'll have to turn that into a video response where I'll go back in and do that at a later time. Okay. So if you guys are ready, let's get into it. First thing, you need to make sure that you have your pen, of course, your paper with your notes, anything that you're taking notes on. Okay. And of course, you need a calculator because we're going to be doing a lot of calculations. And sometimes I need you guys to back me up in terms of the numbers that you may see. Okay. Sometimes these numbers come off wrong because I am writing them down, trying to get the notes down. And sometimes looking at the screen will throw me off a little bit. So if I'm not answering your questions right away, please don't hold it to me because I'm trying to make sure I get them in, as we go along. So let's go ahead and start with the gas laws. First off, when it comes to the gas laws, there are different things that you need to know. The different units that you all will be affiliated with, of course, entails kilopascals, millimeters of mercury, a torr, pounds per square inch, or PSI, or or even atmosphere. This middle column here are the main conversion factors that we tend to use. So I know that 1 ATM will always equal to all of these units right here. 101.3 kilopascals, 760 millimeters of mercury, also 760 torr, and 14.7 PSI, or pounds per square inch. So in a lot of your problems, when you talk about the gas laws, you want to make sure that your pressure units are the same, okay? So let me kind of give y'all another example too, in terms of how we can apply pressure units. So for instance, recently I got a tire, a hole or a nail, excuse me, stuck in my tire. So when I opened you guys up with this video here, I actually was showing you all this video here, and let me share it with YouTube so they can see it too, okay? So I was sharing this video because I want you guys to see how the gas laws actually worked in terms of my car. So I had a hole in the tire and I had to get air put in it. So as you guys may or may not know, the pressure of your tires, as you got, let me zoom in so y'all can see that, okay? It's kind of blurry right here, but it's PSI, pounds per square inch. Here's the deal though. I'm going to see if you guys can figure out which tire was actually in trouble. Okay, so let me just kind of play this quick thing so y'all can see. All right. Look at the tires, and I'm going to see if you all can tell me which tire seems to be like off the meter. Now, if you take a look, there's one that's 32, the top left is 32 meters. The top right is 28, I said meters, pounds per square inch. The top right is 28 pounds per square inch. The back left tire was 29 pounds per square inch. And the back right was 27 pounds per square inch. Which one of those do you think actually had the nail in the tire? Showhog, how you doing today? Did you get my video that I did for you? I did a video response for you, and I want to make sure that you got it. And if you did, just give me a thumbs up, Showhog. I just want to make sure. It was last week sometime. Yes, the 27 pounds per square inch, that one is the one that's low. Okay, yes, please do, sir. Please do, because I made a video response for you. I try to tag you in it, but yeah, it's like, I think like maybe 2 videos back. And it dealt with enthalpy. That's what we were talking about last week. So on this part, it was like, I think Wednesday. Yeah, it was Wednesday when I did it for you, Wednesday. So the back right tire was the one that had all those issues, and we had to put air in the tire. So I'm going to play it again, and now you're going to see what happens when we put air in it. Watch those numbers. Okay, the top left, of course, is getting higher. And then we were going around and putting air in all the other tires. And as you can see, it went out of the red and now it's, in the white. And now if you notice with the tires, okay, they're all trying to get in alignment with each other. And when you have pressure in your tire, here's what you got to remember. If the pressure goes up, the volume will go down. If the volume increases, the pressure will go down, because it's what's called being inversely proportional to each other. So let me go ahead and go back to my other screen so you guys can see what I'm talking about as it relates to these whole gas law problems, okay? So whenever you're doing pressure and volume, your pressure units have to be in the same unit, okay? So when we're talking about, let's say, Boyle's law, and you're dealing with 2 pressure units, if one of the pressures is in ATM and the other pressure is in, let's say, pounds per square inch, you've got to convert one to the other. Now, in what I'm doing right here on the screen, though, I'm just going to start off with the basics and show you guys how to actually convert. So in this first problem right here, okay, I'm going to zoom out a little bit so you all can see this. It says An oxygen tank contains oxygen at a pressure of 2.00 atms. What is the pressure in the tank based on the following units? Okay, so what we got to do is figure out what is the pressure in the tank based on the following units. So all you're doing is taking the 2.0 atms and you're just going to convert that to a torr. So you would have to go back to your chart. This chart is going to tell you how to do that. Okay, all you need to do is take the 2.0 ATM times. Now, remember, on the very top, since we're getting into a torr, I'm going to put 760 torr on the very top. And on the very bottom, 1 ATM. So I'm actually using this particular conversion factor right here. The 1 ATM equals 760 torr. So on the very bottom, of course, I'm going to write 1 ATM. Now, for my answer, okay, the answer in terms of significant digits is not based on the units that you see here or the numbers here. It's based on the value that they gave you in the problem. So for this one right here, where I have 2.00 ATMs, I am going to have you guys put the answer in 3 significant digits. So what we're going to do is we're going to take the 2.00 times 760 torr, and we get 1520. Okay, that is also equal to 3 significant digits. And of course, we're going to cancel out our ATMs, and we're going to end up with 1520 torr. Now, if I told you to put your answer in 4 significant digits, you could add the decimal to the end of that number, and that would give you 4 significant digits, okay? But in this particular case, our answer is in 3 significant digits, and this is what we have as a result, 1520 torr. Now, let's go to the next one, because remember, when you're talking about pressure units, a lot of times you think about PSI dealing with tires, but when you think about millimeters of mercury, that's often associated with a blood pressure pump, okay? So if you ever have to get your blood pressure measured, it's usually measured in millimeters of mercury, FYI. Speaking of millimeters of mercury, here's your next problem. So in letter B, you're going to take that same number, the 2.00 ATM, and you're going to convert that to a millimeters of mercury. So what we need to do, of course, put 1 ATM on the bottom. So what I'm writing in black will never change. But on the very top, the unit that I'm going to is millimeters of mercury. So I'm going to use 760. So guess what? It's going to be the same answer as we had in torr. So torr and millimeters of mercury are pretty much the same thing, okay? The same thing. So all I have to do now is just put my answer here, 760 torr for my conversion chart, okay? And again, multiply those two numbers, and you're going to get the same number from before, 1520 millimeters of mercury, okay? 1520 millimeters of mercury. We're going to do another one, okay? Because they're that simple. When it comes to the conversions, they're just this simple, okay? I promise you, it's nothing hard about this at all. You just have to know which unit to use and which one to convert to, and that's it, okay? That's it. So let's say that we're going to do this last one right here, where we're going to convert, again, still 2.00 ATM, and we want to convert that to kilopascals, kPa. Well, guess what? We're going to go back to our chart. And according to our chart, 1 ATM is equal to 101.3 kilopascals. So we're going to actually use this first one right here, the 101.3 kilopascals. And I know that's a little back. So let me zoom in so you all can see that, okay? So that's 101.3 kilopascals. So I am going to place that number on the top, okay, right there. Let me zoom back out a little bit so y'all can see that, okay? So on the very top, I'm going to put 101.325 kilopascals. And again, you're crossing out your ATMs because we do not need that anymore, okay? Again, this is a chart that's found in most chemistry books, okay? 101.3. Let me get rid of the 0.25, that 25 part. Okay, so right here again, 101.3. Okay, now what am I going to do? I'm going to multiply those numbers again. 2.00 times 101.3. And we get 202.6. So again, we need 3 significant digits. So although we have 202.6, we need to round it off to 203 kilopascals to give us the 3 significant digits right here. Okay, so 202.6 becomes 203 kilopascals. Okay. The reason why, again, I'm going through this is because some of your problems may give you 2 different units of pressure, but you have to make sure that they're both in the same unit, not one being one thing and one being another. They must be in the same unit, okay? Same unit. Now, I gave you that information because now as we go through gas laws, we're going to hit the first one, Boyle's gas law. Think about your lungs, okay? If any of you guys are asthmatic, you may have problems right now with all this pollen. Like the volume of your lung capacity may be diminished, or it may feel like it's being diminished because of the air pressure, the barometric air pressure surrounding us with all this pollen. Soda, if I shake a bottle of soda and I open it, guess what's going to happen? All that pressure is going to be released as a result of the pressure increasing because of the volume. Of course, swimmers use their lung capacity blowing through a straw. That's pressure. Now, you're probably saying, all right, well, how does this relate to what I'm going to do in my daily life? Well, here's an example. Again, what I just told you about with those tires. On a hot day, the air pressure in your tires can increase or decrease. Same thing with your cold days, okay? The pressure of your tires can change based on the temperature outside. So when you talk about Boyle's law, you're describing the inverse relationship between the pressure and the volume at a constant temperature. So here's something you got to remember too, okay, just to kind of help you guys figure this out. Whenever somebody says something is inversely proportional, that means if one goes up, the other one will go down. So if I increase my pressure, my volume is going to drop. But if I decrease my pressure, my volume is going to increase. And the typical graph that looks like Boyle's law is a little curve because they're inversely proportional with one another. That means they're opposites, okay? The formula that's associated with Boyle's law is this one right here that I'm going to highlight. P1 times V1 equals P2 times V2. And we're going to use that formula for these gas laws so we can solve them. Now, again, if you all are like need a better understanding about the gas laws, particularly Boyle's law, here's another example, okay? Let's say that you are packing a bag, okay? And you got a lot of stuff. Like if you're going on a trip and you're packing your suitcase, if you are putting a lot of stuff in your suitcase, eventually that suitcase is going to pop open because it's going to increase the pressure, okay? So, or decrease the pressure. So in other words, as you put a lot of volume in that suitcase, the pressure is going to drop and it's going to pop, okay? That's another way to think about it. Or think about a balloon. If you blow a balloon up and you're increasing the volume in the balloon, then the pressure is going to decrease. But if you increase the pressure, the volume is going to decrease, okay? So here's a word problem to kind of help you guys remember this, okay? Here's a word problem. Let's say that you have a sample of nitrogen that's collected in a lab that occupies a volume of 725 milliliters at a pressure of 0.971 atm. What volume will the gas occupy at a pressure of 1.40 atm, assuming that the temperature remains constant? So here's what you're going to have to do. You're going to have to, again, know that this is your formula here. P1 times V1 equals P2 times V2. But as I tell my students all the time, you can easily predict the answer if you do this. You're going to say P1 equals, and then P2 equals, V1 equals, and then V2 equals. So let's say that what they gave you in the problem first, they gave you the volume of 725 milliliters, and the first pressure reading was 0.971 atm. Let's write those numbers down. P1 again was 0.971 atm. V1, 725 milliliters. What volume, so you're looking for your volume, okay, you're looking for V2, will the gas occupy at a pressure of 1.40 atm? So here is the catch right here. Notice how your pressure increased. So since your pressure increased, you know that your volume is going to decrease. So your answer that we're going to predict is going to be less than 725 milliliters, okay? That's how you're going to know what your answer should be. So if you're given these examples on your test and you have to predict what the answer will be, all you got to do is know that if one goes up, the other one goes down. So in the case of my pressure, the pressure increased. That means I have to look for an answer that's less than 725 milliliters. That's how you can predict your answer off top. Now, because I want to know what formula to use, okay, we're looking for V2. So I'm going to highlight that here. We're looking for V2. So to isolate V2 and get that by itself, I'm going to simply divide both sides by P2. And that's my formula right there. V2 is going to equal to P1 times V1 over P2. So now all I'm going to have to do is plug those values into my problem. So I'm going to go back up here, okay, and look at my numbers. So here's my formula. V2 equals P1 times V1. So P1 was 0.971 atm. Your V1 was 725 milliliters. And then your P2 on the very bottom was 1.40 atm. So let's go ahead and get rid, of course, our ATMs, slash those out. And now all you have to do is just go ahead and plug the numbers in. 0.971 times 725 divided by 1.40. And I get 503. The answer on my calculator is 502.8, but we only need 3 of those significant digits. So my answer becomes 503. And remember, we said that we were doing what? Finding the number that was less than 725. And that's how we ended up with 503 as our final answer. Okay? So that's how you do that type of problem. Now, you know, when it comes to word problems, all you have to do is make sure that you're able to read through the problem first and then determine what did they give you in the problem so that you're able to solve it, okay? So I'm going to go to the next problem. Right here. It says, a chemist collects 59.0 milliliters of sulfur dioxide gas on a day when the atmospheric pressure is 0.989 atms. On the next day, the pressure changed to 0.967 atms. What will the volume of the sulfur dioxide gas be on the second day? So I just read to you what was given in the problem, but let's now identify what we need in terms of the numbers. Here's the first volume reading here, the 59.0 milliliters. The first pressure reading was 0.989 ATMs. The second pressure reading was 0.967 ATMs. What they're wanting is the volume on the second day. So again, I'm going to plug in what we know, P1, V1, P2, V2. So P1, 0.989 ATM. P2, 0.967 ATM. So already we know that our pressure has decreased. So since our pressure has decreased, what is your volume going to do? We already know it's going to increase. And they're looking for V2 because they said on the second day, what will the volume be? The volume that they gave us for the first day was 59.0 milliliters. So again, if we know that our formula is P1 times V1 equals P2 times V2, and we're trying to solve for V2, like we said before, you isolate V2 and divide both sides by P2, okay? So that you know to get V2 by itself. So now my formula is going to be equal to V2, okay? Let me scoot this one down a little bit. Uh-oh. Hold on, let's see. There we go. So I'm going to go ahead and plug in my formula, okay, which is V2 equals P1 times V1 over P2. And again, all we have to do is go back and look at our numbers, okay? So P1 was 0.989, 0.989 ATM times V1, which is 59.0 milliliters, and my P2 was 0. Let's go back and look at it again to make sure, 967, okay, 0.967 ATMs. Again, all you have to do is cross out the ATMs because you don't need that anymore. And so now your V2 is equal to those numbers. And remember, we predicted what the answer should be because we know that the pressure dropped, but the volume is going to increase. So the number that we're going to assume that it's going to become is greater than 59.0 milliliters. So whatever we calculate, our answer has to be greater than 59.0 milliliters. Let's plug it in to make sure. 0.989 times 59.0 divided by 0.967. And what do we get? 60.3. Those are our, hello, what's up, March Revolution? How you doing? So our answer is 60.3 milliliters. And again, if we go back to look at what we wrote down before, the answer has to be greater than 59.0, and we do. And we did. We ended up with that number. Okay. Any questions so far from anyone based on what we're doing so far? Yes, gas law problems about the bomb.com. They're not that hard. I mean, you got to know how to, just use the formulas that are given and roll with it. Again, for Boyle's law, P1 times V1 equals P2 times V2. 59.0 Starlift Hollywood was given in the problem. Let me go back so you can see it. Good question. In case you missed it, it was given in the problem. Right there. Yes, Shohad, you can say that. Yeah, that and the PV equals nRT is the ideal gas law. And yes, because you can also have what's called the combined gas law also from that. So yes, technically, yes, that is correct. That is correct. So here is our next problem. Okay. Again, sometimes when you read these problems, you got to read them twice. You're welcome to make sure you got what you needed. It says, to what pressure? So you're looking for that. would you have to compress 48 liters of oxygen gas at 99.3 kilopascals in order to reduce its volume to 16.0 liters? Okay, again, at what pressure? So P1, P2, B1, B2. Okay, at what pressure would you have to compress 48.0 liters at 99.3 kilopascals in order to reduce its volume to 16.0 liters? Okay, now I wrote this information out, okay, but I'm gonna read it again. It says, to what pressure would you have to compress 48.0 liters of oxygen gas at 99.3 kilopascals in order to reduce its volume to 16.0 liters? So right there, they told you to what pressure would you have to compress or decrease. So you need to find out what is the initial pressure. They told you the volume initially was 48.0 liters. It was reduced to 16.0 liters. So guess what? Our volume did what? Our volume decreased, so our pressure is going to increase. So in other words, the number that you get right here, guys, that what we're looking for has to show that it increased to that number right there, the 99.3, okay? So in other words, you're looking for P1. So I'm going to isolate this formula right here, the P1 V1 equals P2 B2. And what I'm going to do is say, because remember, I'm going to divide both sides by V1. So P1 equals P2 times V2 over V1. Okay, that is the formula that we're going to use. And we're just going to go ahead and plug in the numbers that they gave us right here. Okay, P2 was 99.3 kilopascals times V2, which is 16.0 liters. All of that over 48.0 liters. Now, here's a thing that you can think about, okay? I love to kind of guesstimate numbers. And I know from looking at this that my volume decreased by a third. See, 48 drops down to 16 by a third. If you divide 48 by 3, okay, you get 16. In other words, if I would have reversed this, I could say that my volume tripled. But in this case, it actually decreased by a third. So since this decreased by a third, you know what's going to happen to my P1? This means that the pressure triples, okay? So I can guesstimate that my answer here is going to be like 33 something. It's going to be like 33. But again, if you want to prove the point, let's plug these numbers in. 99.3 times 16.0 divided by 48. And there it is right there, 33.1. And again, you're probably saying, well, how did you get that? Because, let's cancel out our like terms. Liters goes away. Kilopascals. How did I get that? Because remember, it's all math, y'all. It's all math, meaning because I know that my volume dropped, it went from 48 to 16. Mathematically speaking, it decreased by a third. Since my volume decreased by a third, then that means my pressure is going to triple. So whatever this initial answer is, it tripled to 99.3. And the number that we got was 33.1. That's it right there. So those are just, a few examples that deals with Boyle's law. Now let's talk about Charles' law. Charles' law deals with volume and temperature, okay? So if you take a look, I got two different pictures here, excuse me, as an example, okay? And You notice this is a hot air balloon, okay? And you know it goes up in the air according to temperature. So you got to have heat, to get this balloon off the ground. As the volume increases, the temperature increases. As the volume drops, the temperature drops. So this is an example right here using a balloon. If you take a balloon, you blow it up. Both of these balloons were the same. But the moment you put ice water to that balloon, it shrinks, it shrivels. But if you add boiling water to the balloon, it increases. So as the temperature increases, the volume increases. So for Charles' law, they are directly proportional to each other. So I'm going to write some little notes over here off to the side so that you guys can see that, okay? So again, with Charles' law, it just simply means that as the temperature increases, the volume will also increase. As the temperature drops, the volume will also drop. They are directly proportional to one another. So if you were to look at a graph with Charles' law, it would illustrate a straight line. And your temperature also must be in Kelvin, okay? Your temperature must be in Kelvin. So that means that if they give you degrees Celsius, you're going to simply add 273 to that value, okay? So again, if they give it to you in Kelvin, okay, I'm sorry, degrees Celsius, you're going to simply take the Kelvin and add 273 to it. Some books will say 273.15, tomato, whichever way you want to say it or do it is fine. Okay, so now let's do a problem dealing with Charles' law. Okay, so I did not type out one for this one. So what I'm going to do, I'm just going to read one out loud. Matter of fact, so again, on YouTube, you guys can't see it, but I'm just going to type it out so that way you guys can see it, okay? Because I don't want to neglect y'all on YouTube. So here it is, a container of, I'm going to type it out real fast. I'm going to type really fast. A container, and I'll zoom in so y'all can see it on TikTok. Okay. A container of oxygen has a volume of 349 milliliters at a temperature of 22 degrees Celsius, okay? So let me find the little degrees Celsius. We're just gonna put the little degree symbol and see. That's degrees Celsius, okay, for the sake of typing everything out. Okay, what volume will the gas occupy at 50, and there's a decimal on the end, degrees Celsius, okay? Now, here is the deal with this particular problem. This is what we got. We have to know that when we're dealing with Charles' law, okay, Charles' law is V. Well, I like to put the T first because it's almost like saying TV. So for Charles' law, it's T1 times V2 equals T2 times V1. Okay, T1 times V2 equals T2 times V1. If you can remember that, you're good to go. Now, what you're going to do is write out everything that you know from this problem. Okay, we're going to set it up the same way we've done the other ones. T1 equals V1 equals. T2 equals V2 equals. All right, the first temperature reading that they get, well, let me go back to the problem. You have a volume of 349 milliliters, 22 degrees Celsius for that. What volume, so you're looking for V2, will the gas occupy at 50 degrees Celsius? So what we're going to have to do is write again. The T1 that they gave you was 22 degrees Celsius, but we're going to have to add 273 to that number. They also gave us 50 degrees Celsius, okay? And again, we're going to have to add 273 to that number. They gave us the first volume reading of 349 milliliters. They're looking for V2. So I know that because my temperature increased, my volume is also going to increase, okay? So because my temperature increased and my volume increased, that means that the number that we're predicting for my volume to become is going to be greater than 349 milliliters. Let's go ahead and add 273 to both of these numbers here, both of these temperature readings, okay? We got to add 273 to both of them. So again, 22 plus 273 gives me 295. So that's 295 Kelvin for the first number. And the other one is 50 plus 273, and we get 323 Kelvin. Okay? So those are our new temperature readings, because remember, in order to apply this formula, you've got to place your temperatures in Kelvin. And because we're looking for V2, we're going to isolate this formula by crossing out the V2. And then we're going to do what? Divide both sides by T1. So basically, you're saying V2 equals T2 times V1 over T1, okay? That is your formula right there. V2 equals T2 times V1 over T1. Now, I'm going to plug in the new number for T2, which is 295 Kelvin. My V1 is 349 milliliters, and my T1 is 323 Kelvin. Of course, you're going to cross out the K's because you don't need those anymore. And let's plug it in. 295 times 349 divided by 323, and we get 319 milliliters. Okay. Oh, hold on. Something's wrong. Let me go back and double check these numbers again. Because again, remember, the V2 has to be greater than 349. So T1, oh, you know what? I see my mistake. Ooh, there we go. T2 was 323. And this is a teachable moment right here, guys, so you all can see how to pick up your mistake. I have put in T2 being T1 on the top. That's how I knew something was wrong. When I got my answer and the answer was 319, I said, wait a minute. It has to show that it increased. Okay, so that's how I'm able to identify the mistake. T2 was 323. That's on the top. T1 was 295. That's on the very bottom. 323 times 349 equals, and then you're going to divide that by 295, and I get 382. There we go. V2 is equal to 382 milliliters, okay? And that answer was correct in terms of being greater than 349. So that is our answer, 382 milliliters. Okay. We'll do one more of these Charles problems, okay? Just to make sure that you guys are good to go when it comes to these two gas laws. Now, you will need to know these things when it comes to, of course, your combined gas laws, Gay-Lussac's law. All of them are slightly different, but they operate in similar fashion. Also, you'll need to know the gas laws, because when you deal with, let's say, molar volume, okay, you're going to have to use that law for that particular purpose. Okay. Dalton's law of partial pressure. You're going to also have to use these laws accordingly. So when it comes to the gas laws, you've got to do several things to make sure that they work. Okay. So we'll do one more of Charles' law before we get out of here. Okay. So let me find a good one for you guys. Let's see. Okay. For this one, I'm just going to write it out because I don't have time to type it out. I'm just going to give you I'm going to verbally tell you what it says, okay? And I want you all to hear what I'm saying and tell me where the numbers are going to go, okay? All right, so we're dealing with Charles' law again. T1, V1, T2, V2. Okay. A balloon full of air has a volume of 2.75 liters at a temperature of 18 degrees Celsius. What is the balloon's volume at 45 degrees Celsius? Okay. A balloon full of air has a volume of, so I'm going to put that number there, 2.75 liters at a temperature of 18 degrees Celsius. What is the balloon's volume? So you're looking for V2 at 45 degrees Celsius. So again, you guys know what you got to do, right? You've got to convert the temperatures to Kelvin. So all I'm going to do is add 273 to both of them, okay? I'm adding 273 to both of them to get the answer in Kelvin. So 18 plus 273 gives me 291, okay? So this is 291 Kelvin for the first temperature reading. And for the second temperature reading, 45 plus 273 gives me 318 Kelvin. Okay, we're looking for V2. So again, if we go back, okay, up here to our original problem or formula, and we're looking for V2, remember, V2 is equal to T2 times V1 over T1. Okay, so again, V2 equals T2 times V1 divided by T1. So I'm going to go ahead and plug these numbers in. T2 was 318 Kelvin. V1, 2.75 liters. And T1, 291 Kelvin. Now, before we predict what the answer should become, 291, sorry. Before we predict what the answer should be, let's remember, our temperature did what? It went from 291 to 318. Therefore, our temperature increased. So you know what your volume is going to do? It's going to also increase. And because of that, the answer that we get is going to be greater than 2.75 liters, okay? It's going to be bigger than that. So let's go ahead and solve this problem and make sure that we're on the right track. So Kelvins cancel out, okay? And now we're going to go ahead and plug these numbers in. 318 times 2.75 divided by 291, and that gives us 3.01. 3.01 liters. So that is your volume there. And it did increase, and it was greater than 2.75. Okay? So guys, this is it. Like, that's all you have to do when it comes to these gas laws. Charles' law and Boyle's law are very pretty much consistent with each other. All you have to remember to do is to manipulate the formula to solve for it, okay? That's all you have to do. And I may do a video on how to find the other formulas when you're given just one of them. So I may do that one also, okay? Thank you guys so much for hanging out with me this afternoon. I will see you guys tomorrow. Take care.